How'd you do? Looking at the definite integral from 0 to b of c dx, where b and c are fixed real numbers, the first thing you should have noticed was that your integrand was the constant function f of x equals c. Let's just draw a picture of it to get an idea what's going on. That, assuming that c is positive, we can draw it as the constant horizontal line at y equals c above the x-axis. Now our limits of integration go from 0 to b, so we are looking for the signed area between 0 and b underneath the line y equals c. If we're going to use a Riemann sum, we would break it up into n equal width rectangles. The rectangles would have a width of b divided by n, and for each rectangle, its height is c, because the function's constant, times its width, which is b over n. Now, this is our Riemann sum in n subdivisions. Notice in the summand, k isn't involved anywhere at all, so when k equals 1, we would be adding c times b over n. When k equals 2, we will be adding c times b over n. When k equals 3, we will be adding c times b over n. All the way up to when k equals n, we will be adding c times b over n. Adding all these up, that's the same thing as c times b over n times. So we'd be multiplying by n, the n's cancel, and we get c times b. But you and I knew the area of this rectangle is its length times its width. Its length was b, or maybe this is its width. Its width is b, its height is c, so the area of this rectangle is definitely c times b, but we can see it showing up in the Riemann sum, which is sort of encouraging that it matches our intuition. Just to be pedantic, the definite integral from a or 0 to b of c dx equals the limit as the number of subdivision goes to infinity of our Riemann sum that we just computed. That Riemann sum is always c times b, and notice there's no n involved in this particular expression, which means that the limit also has a value of c times b. So for sure, we can say the definite integral is c times b. For the next problem, our integrand is the function f of x equals x. That is a line of slope 1 that goes through the origin. And we are looking for the area, the signed area under that curve between 0 and b. So again, we have 0 and b. So our signed area, you'll sort of visualizing it, we see that that is in fact a triangle. So rather than going through the Riemann sum this time, let's just say, ho-ho, I'm just looking for an area of a triangle, and write the answer down. So the definite integral from 0 to b of x dx is a number, because b is a number. It's going to be 1/2 the base. The base has length b, and the height, which also has length b. So it's 1/2 b times b, which is 1/2 b squared. So I'd like to return to the question on page 6 of computing the approximate signed area under the curve of f of x equals 1 minus x squared between 0 and 3. And now, rather than using 6 subdivisions as we did on page 6, I'm asking that we use the definition of definite integral as the limit of a Riemann sum as the number of subintervals goes to infinity to compute the area exactly. Let me get us started. So, in other words, let me say this one more time. We're going to use the definition that involves limits and Riemann sums with n subdivisions to compute a definite integral. Let's get a picture of what's going on here. Here's our function, 1 minus x squared, and based on the approximations we've done before, we expect our answer to be negative. That's good, right? And this particular problem asks for the upper sum. Now, we've been using left endpoints and right-hand endpoints. What the upper sum means is on a particular interval, we want to use the maximum output value as the height of our rectangle. Because this particular function happens to be decreasing, it will be true that the maximum value will always occur at the left-hand endpoint. So when we set up our Riemann sum, we know the length of the interval is 3, and we're breaking it into n subdivisions. So delta x is going to be 3 over n. And we want to take the limit as the number of subintervals goes to infinity of the Riemann sum Rn. That's the sum as k goes from 1 to n of the function evaluated at, in this case, the maximum value on the kth interval times delta x. The maximum value occurs on the left-hand endpoint, so it will be 0, 3 over n, 6 over n, 9 over n, and so on. So if we write this as the limit as n goes to infinity of the sum from 1 to n of f, now I want, when I plug in my first subinterval when k is 1, I want the answer to be 0. So do you see that's why I need the k minus 1 here times 3 over n rather than just putting a k times 3 over n. And then our delta x is 3 over n. Now, I want you, the rest of this is algebra using summation notation. I want you to try and simplify it on your own. Pay attention to where the indexing variable occurs and take your limit. Once you've tried or once you've gotten frustrated, come back to the next part and I will go through all the nitty-gritty details. But I've got to tell you, it's really tiresome, but you should see it once in your life.